Hello. Thank you, guys. So this is a project that we started at IBM. It was kind of getting pieces from multiple places, you know. And it's a small team. It's not a big product or anything, and we wanted to put in open source from the start, right? And its intent is to make it easier to run the same popular tools that you guys always run in your day-to-day, right? And in Power Systems. Just out of curiosity, who here in the room has ever heard or know what a power system is? Okay, yeah, more than expected. So power is a different architecture. Everybody is familiar with x86, AMD 64, etc. So these are CPU architectures, right? So power, a long time ago, was derived from RISC 6000 architecture. So it was supposed to be a reduced instruction set. With the years later, it evolved, and it started to get closer and closer to the Intel and AMD architectures, right? It was more CISC architectures. So it transformed over the years. And it powers a lot of the older systems from IBM that used to run AIX. I guess AIX a lot more heard about it, right? And a few years ago, IBM kind of changed kind of enhanced the architecture, the low-level architecture and the power systems to also run Linux. So the way that you organize the data matters, right? So the older legacy systems from IBM, they used to have a data organization called Big Endian. So it's most significative byte first and the lower significative byte later. So in order to make it more compatible with the Intel Word and everything else, so they started supporting Little Endian as well, which is what Intel supports, right? So I'm going to give a brief introduction about why Power is used in some workloads, what's the motivation and everything. And let me just show the agenda. So this first introduction, a little bit more about why Power is popular with some types of workloads, right? Later, I'm going to talk of a special component. One of the components that we pulled was related to a project that we had with the Coral project. So this is a collaboration between three big laboratories in the United States. So they got together and they designed and they put together a bid for a supercomputer for processing civil and military applications, right? So I'm going to talk a little bit about the supercomputer and what this component is used for in there. And later, I'm going to talk about, okay, so then we extract that component, a few components from other places, and we kind of carved together and we created this open project, right, which is with the intent of running the exact same tools that you guys already run, but on this platform and making sure that there's a low cost of entry for the platforms. And then if there is time, and if the VPN collaborates, then I'm going to just show some of the dashboards that we put together, right? These dashboards are interesting because they combine both data that is out of band and in band. Out of band is data that you collect from the firmware directly, right? And in band is data that you collect from agents running after the operating system boots up and everything. So I'm going to show telemetry, logs, alerts, things that come from both kinds of data, right? And the end, just what are our plans for the future, right? And questions and answers, of course. So I have to time the presentation so we get time for questions and answers. So first slide here is why Power is popular for certain workloads, right? So one of the biggest draw of this platform is the way that the architecture, the buses and the communications internally, it's compared to what AMD and Intel are doing nowadays, right? We get more speed, more I/O speed out of this architecture. So you can see that there is a much more powerful bus between the CPU itself and the GPUs, right? So 3 channels of 25 gigabits per second. And then there is a special protocol between both CPUs. So there are models that you have 2 CPUs and models that you can get up to 4 CPUs, right, in Power Systems. There is a direct attached to memory at 170 gigabit per second, so it's super fast as well. So things that need a lot of bandwidth between the GPUs and the CPUs and between the memory and CPUs, usually Power has a better cost benefit. Again, for certain workloads, right? So workloads that you process a lot of data in memory, or you take that data to be processed by the GPUs and then you get results back. So this kind of data is conducive on this platform, right? And there's a few other statistics. For those who don't know, in Intel, you usually have 2 threads per core, right? In Power, you can configure that. You have symmetric multiprocessing. So you can have from just 1 thread or up to 8 threads per core. So you configure way you want it, and depending on the application as well. If you count the bus speeds and everything that I showed before and compare to same generation on Intel, I didn't do the count myself, but what they advertise is 9.5x. I think this is an average getting the speed between the GPUs and CPUs and memory speeds and everything. So they do an average, can get up to that. And because of the speed on the memory transfer, you can get more memory as well. And another thing is, I don't know if that matters, but it was the first platform to deliver PCI Express Gen 4 speeds, right? So I guess they called it out to show that it's always, we're always trying to innovate in this platform. We're always trying to bring the biggest benefits in I/O and memory bandwidth, right? So that's a very brief introduction for Power. So if anybody asks you guys, you cannot say you never heard about it anymore. Okay, so now I want to talk a little bit, just some fun facts, right? About there is a project called Coral. It's short for collaboration of Oak Ridge, Argonne, and Lawrence Livermore. These are 3 big laboratories in the US. They do stuff for the Department of Energy and a few other departments in there to do research on simulations for nuclear weapons. They do, of course, there's a lot of civilian research done as well. Things that you need to process big data on Hadoop or Elastic is very much used there as well for data processing, right? And there are several other workloads that are in this area for AI, analytics, big data, right? So it's all the workloads that like the Power Platform, right? So when they brought this project, IBM had a few partners and they won this bid for producing these supercomputers. So there are 2 today. And up to, I'm not sure exactly anymore, but up to the beginning of the year, Summit was the fastest one in the world, right? If you get In terms of operations per second, was the fastest. So Summit is the biggest of the two. It's located in Oak Ridge in Tennessee. And there is the Sierra model. It has the same number of nodes, but it has a node that is a little bit less capable than the Summit computer. And this Sierra one is located in California, Lawrence, Livermore. And it mostly does nuclear simulations, things like that, right? And the one in Tennessee is more used for civilian applications. Was the first computer to reach exaops performance. So exa is the 10 to the power 6, I believe. And then there are some fun facts. The Summit itself, only the Summit, has 185 miles of fiber optic interconnecting the nodes. There is a lot of floor space. You can imagine that that takes a lot of power consumption, right? There is a lot of cooling involved to cool all this hardware. There's 340 tons, not only the hardware, but also the auxiliary assets that they need to have in a data center, right? Power supplies, transformers, all that kind of stuff. And then the computer, the supercomputer itself, it's a bunch of nodes connected together, so it's 4,600 nodes. There's 6 GPUs per node, and you can make the calculations here. It gives 27,000 GPUs, right? So that's a lot of processing power. Has 200 gigabytes of bandwidth between the nodes. It has 200 petaflops, and like I said before, the actual ops performance varies per application. So it reached up to 3.3, if I'm not mistaken, 3.3 exaops on doing genetic simulations and things like that. So depends on the application. It varies between 1 exaflop and 3 point something exaflops. All right, so this is just some. This was an article, actually. I thought it was interesting, so I brought it here because it is directly related to this data that we help collect from the firmware. This component that we implemented for them, it's called Crassd. I have a chart later. Next chart is about it. It collects things like temperature, current, the voltage, the fan speed. So they collate all this data that they get from their cooling equipment, and then they intelligently they vary those. They tweak those parameters, right, to make sure that the cooling is just appropriate for what is running on the platform at any point, right? So with this intelligent cooling system, cooling tweaking, they got from 13 megawatts, I think, was the, let me see. Yeah, 13 megawatts. They got down to 10.1 megawatts in average. So they're saving a lot of power there. There is a list called Green 500 class. It's one of these big computers where they try to beat each other. Which one saves the most power per petaflop of speed, right? Summit was the #1 until earlier this year. I think it's #2 right now. But the #1 is a much smaller computer. It's a computer in NVIDIA. I think it's 1/10 of the size of Summit. So it's a great accomplishment being in this category of big computers and being able to save as much energy, right? Okay, and then there's a few other, so this is a person from Oak Ridge Laboratory, the person who is actually responsible for maintaining the supercomputer and doing the operation, right? So she published this article in HPC Wire's magazine for high-performance computing, if you guys don't know about it. It's an interesting reading. But I just put the link here if somebody wants to follow up and read more about it. Now, a little bit more about the kind of the architecture, how the nodes are interconnected, and where this monitoring is running, right? So usually in high-performance computing, I mean, there's not a lot you can vary. You have lots of racks with lots of nodes crammed into them. Usually you have storage racks that are separated, but interconnected through the same InfiniBand, right? And then you can have management nodes where you run your applications and where you kind of drive the applications that go into the actual nodes for processing, right? So in this case here, you guys can see there is what we call service node. These numbers that you see there, SN01, 02, up to 16, right? So these are service nodes, and they're double linked to collection of 16 racks each. So each of the 16 racks have 18 nodes, I believe. So it's easy to do the calculation. 18 times 16 times 16 collection of racks. It has to be 4,000, and that other number that I showed here is 4,608. It's probably 18. So they're double linked. If one of these service nodes goes down, so the other one takes over. The monitoring is a little bit degraded in that case until they fix the other service node that goes down. It rarely happens. I think I heard about 2 occasions only, and one was planned that they had to do that. But in these service racks, so they run this component that goes and monitors the firmware for every single node. So it goes to all the 16 times 16 times 18 nodes. Each one has a firmware, and each one subscribes telemetry. So they collect the telemetry and they aggregate it, and then they take it out to that big data store, the right side, right? And there's other things that are monitored as well. I'm not going to go into a lot of detail, but ESS is Elasticsearch. It's another product that you can aggregate and you can manage and monitor metrics from storage, right? There is other stuff that Oak Ridge itself is running that we don't even know about. So in this presentation, the focus here is just to tell how Crassd is running and is situated in this design, right? Okay, so now it's a little bit more busy chart here, but this is more or less how the monitoring works. So each computer node here, you have the onboard controller that connects to the main memory, connects to the GPUs. Then there you have the host OS. And there is another product called CSM. I'm not going to enter in detail as well, but this is what in their environment is taking the place of all the goodies, popular tools that we generally use instead, right? So instead of having a file bit or a metric bit or FluentD or something else, they have this product here to collect some metrics from time to time. And then there's Crassd that does the out-of-band data collection directly from the firmware, right? So you can see that the data flows, all the data is taking out to the big data store, and then from that big data store, they process this data together, and they have Grafana dashboards where they see how the metrics correlate with each other, right? But Crassd itself, already envisioning its use in other places, we made it so that you can just drop small plugins. It's really just something that gets the data and puts in a socket and sends it to other applications, right? So you can just drop plugins in Crassd, and it can send to Prometheus or Elasticsearch or other tools out there, right? And then when I talked about the package that we published in open source, it's a different project we call PowerOps, because it incorporates all these open source tools, right? Then I'm going to talk a little bit more about how it integrates with Crassd. Okay, so this is in a nutshell how Crassd works. Oh, one other thing. So Crassd, today it supports multiple protocols to talk to firmware. So there are older ones that, older models of systems that they only have IPMI. I guess you guys heard about IPMI, right? So it's an older protocol. Now there is a new protocol coming into the place of IPMI, but some systems support both. Some systems in the future support only this new one. It's called Redfish. So we're adding support for Redfish now. And the BMC is a special BMC called OpenBMC. OpenBMC, in addition to these protocols, it also has a REST API. So it's amazing what you can do. We can cram into a small firmware, right? But it does have, you can create sensors, and you can specify what's the period that you want the telemetry to be sent back to you. So it's a very, very flexible interface, right? And Crassd makes use of that, makes use of the REST API from OpenBMC. Okay, so now a little bit more about this other encompassing project. So we got Crassd because we saw some potential in it. It's being used in these supercomputers. There is interest from the IBM Cloud. So IBM Cloud, for those who don't know, it's the same. It's the competitor product to Amazon AWS or Google Cloud. It's the one that IBM operates, right? And it has both x86, and now it has Power nodes in there as well. So they got interested, and they are using this technology as well. So internally, you don't see it. If you subscribe to a virtual node in IBM Cloud, of course, it's managed under the covers, right? But the operators inside IBM, they have dashboards where they see the firmware data alongside other data that they collect through the nodes. So it's a big environment as well. So we saw some potential in this, and we wanted to publish in open source, right? And but we didn't want to use these legacy tools like CSM or something that we created out of our own minds, right? So we wanted to use tools that everybody uses day to day. So we started thinking, what's the what's the most popular tools in categories? And then we started doing some integration. So there were other products in open source as well, things that we participated before, where we did monitoring on power systems that gave us some initial. So it made it easier, because if you start to migrate some of these tools to Power, initially they don't work out of the box, right? So some tools you have to compile binaries, you have slightly different metrics in Power, things like that. So There were some other projects that used the Elastic Stack, so we reused that code as well. There was one that was also being prepared for these supercomputers, HPC projects. They were using Netdata, right? So Netdata is another tool that is getting more and more popular. And also on our to-do list is Prometheus and Grafana, which is super popular as well. So it's used in stacks where you find containers or you find virtual machines. OpenShift is using it now, right? So it's super popular as well. So we wanted to get these tools, and those some of these tools are more appropriate for different use cases. So we have a collection of data that you have to hold over a long period of time, so called this historical data, right? Versus more real-time data. So if you look at Netdata, for example, it is more appropriate for real-time because it has several, the dashboards are very dynamic, right? And it's more appropriate for drilling down into a small number of systems, as opposed to Elasticstack, where you have the database behind it. Elasticsearch, we can cram and store a lot of data in there, right? You can configure the dashboards to look over, I don't know, months months of data. So if you want to visualize data that is more historical, you would be more appropriate for using one of those systems instead, right? So we started with this. Elasticsearch has a good handle of historical data, and then Netdata for drilling down into some of the nodes were experiencing problems that you want to see more real-time kind of telemetry in there, right? Then there are some comments of what value putting something like this together brings, right? So somebody that wants to use Power because of all those benefits, processing AI or analytics, you don't have to start putting together, recompiling binaries and repackaging stuff. So this project is supposed to give you a head start, right? Of course, it has only some sample dashboards. You're going to want to configure your dashboards differently, or you want to collect data from different agents and things like that. So, but the good thing is that you don't have to start from scratch. Some specific things that you need to do in order for these tools to work on Power are already built in, and they are already automated as well. So just going ahead, this is what we do for automation. So we didn't want to only produce a set of tools pre-configured and cram them into a Docker container or something like that, right? So we wanted to give you a flexible way to automate deploying multiple environments. We chose Ansible for that. It's one of the most popular configuration management solutions, right? Deployment and configuration manager. There were some assets that are already implemented in Ansible before that I talked about, so we got that for free as well. It kind of gives a head start on how to deploy this into multiple topologies. So we made the playbooks flexible in a way that you can choose if you want to deploy all these tools together or if you want to separate them. So for bigger clusters, usually you have multiple nodes with Elasticsearch running in parallel, right? So you can do that with these Ansible playbooks. So just go there. You specify how many of the nodes are controllers. You specify how to the range of IPs that you want to discover for the endpoints. And you, of course, you have to configure a few other variables as well. And then you click a button and it starts deploying. And half an hour later, it's already and running, and you can point to the browser, right? like I said, this is just a head start. So it comes with some dashboards you may want to configure. May want to collect additional data, but it's a head start, right? So that's the intent of this project, is to get people to collaborate. So if somebody else in the Power community builds integration for, I don't know, another tool like Zabbix, for example, or builds just kind of plugins for Zabbix to get some other kind of data, I mean, something like get information from GPUs attached to Power nodes. So we wanted to have a place where they could go there and drop their stuff, and it would work with other tools as well, right? So that's the intent here. Okay, so speaking just a little bit more about the structure of the Ansible playbooks here. There are three steps. So there's one that we called bring up. So we wanted to support multiple target environments, right? So and by target environment, I mean you could deploy this into virtual machines, I don't know, from KVM, or there is another hypervisor that works on Power as well. It's called Power VM, right? This Power VM is not done yet, but you could just create another role, some basic interfaces that all the roles for bring up have to follow. Drop it here, and then you choose. I want to deploy this into a Power VM infrastructure, right? And then it would just integrate seamlessly here. There is stuff from converged infrastructures or hyper-converged infrastructure. They have REST API, different REST APIs you could use. One of these infrastructures, I don't know if anybody here knows Nutanix. So Nutanix is one such platforms out there, right? So underneath, it's KVM, but they have some nice REST APIs that you can use instead of doing verge commands and things like that to create the VMs under KVM. So, and I mentioned that because this is one of the integrations we already done, kind of reused again from another project, right? But you could put another role here that would create things into Docker containers. And in fact, there is one of my colleagues is working on supporting containers right now, right? Okay, so this is for the deploy. I actually think I went ahead of these slides. So this is supposed to be the picture that talks more about the deploy phase. So it's like I said, you have Ansible roles, special Ansible roles that can deploy to multiple infrastructures, right? And you can just drop another one, and you specify in the variables which one you want to use, and it gets from there. Then the infrastructure, so this IaaS layer, it's called the infrastructure as a service, right? So it's supposed to do the bring up and configuration of the other nodes that are in the architecture, right? So you have three types of nodes then. You have builders, and builder is just a special node because some of these packages and projects, we kind of compile them on, kind of in the middle of the process here, right? So, for example, one example is the Golang package is available on Power, but the Go daemon is a binary isn't, right? So we build a small script just to go and compile the Go daemon and package it for Power, for both Debian and Red Hat packages. So these builders, they compile stuff that is not yet available for Power and take it to a repository that then is used in the other phases, right? Then there's controllers. There's where the server side of the applications run. For example, Elasticsearch, the components running there. The Crassd server. You can run everything in a single controller if you wish, or you can spread over just changing variables in the playbooks, right? And then there's the endpoints. You just define which are the endpoints, the address ranges that you want, and then if it is a virtualized environment, you can even bring up all those nodes and create them as VMs or containers and instantiate the initial configuration for deployment, right? The next session here is, well, I got ahead again. So it's the build phase. So this is the bring up. Here's the build, right? So it's what I said. You build stuff that is not yet available for power. The intention of this is to be temporary. One of the things we want to do, we're a small team, right? But we want to reach out to these communities. For example, the Bits, the Elastic community. Up to V5, it's more or less architecture independent. It's all Java code that runs anywhere, right? But then if you start looking at V7, there is some binaries in there and packages that don't immediately exist on Power. So we started looking into this and how to initially build those packages for Power, right? So it will be part of this section of the playbooks. So it will automate building and packaging those packages for Elastic V7. We're working on that right now. But at some point, we want to upstream this back into the Elastic community, right? So we didn't even start talking to anybody yet, but it was just as an example, right? So as tools get more integrated, we want to consume this directly from the open communities, right? And then finally, the last phase here is the deploy phase. So this basically gets all that was missing on Power on that repository on the right side there. Get those binaries, get other binaries that are already available for Power, and download them from their existing repositories, right? And then it's just on the playbook variables, you define how you interconnect them, how the flow of data goes from one node to the other, and just the deploy phase deploys and configures them and creates the dashboards that we have by default, right? There is a few dashboards, so we're almost to the end here. Then next I'm going to show you there are 4 dashboards right now. One is for metric bit. It's more or less the same as the standard metric bit dashboards, but I did some tweaks on them to be able to work well on Power, right? There is a dashboard, a very simple dashboard I created for getting logs from the most important log files in the Linux systems, right? So like the alt log file, the kernel, the syslog, things like that. There is one metric dashboard for Crassd alerts. So if there is any problem, the firmware, it's going to show as an alert, and it's going to show in Elasticsearch as well. And then there is the Netdata dashboard where you can see near real-time telemetry flowing from Crassd as well. And this is the, so this is not exactly the environment that I'm going to show in the demo, but it's close. So this was the old demo I had. We had to use those systems for another project. So what I did, those two were bare metal nodes where we had Netdata separate from the Elasticsearch, right? They had to be used for something else. So I just created a VM and crammed everything together in the same VM. That's the difference here. And in here, where I have Boston. Boston is a code name for the Power 9, right? So there is a scale up and scale out systems. Boston is a scale out system. So it means that it doesn't, it's more appropriate for enterprise applications, right? And then there's the scale up systems that are more appropriate for high performance computing. So those systems are the ones that are being used in the Summit Supercomputer. It's, their code name is Mihawk. It's Indian. I added 2 Mihawks here just to get telemetry data and show that in Netdata. So it's going to be, it's going to give like different kinds of telemetry than the Boston. Okay, so let me see how we're on time. Okay, just 5 minutes, I think, could give a good idea of the demo here. So this is a system I have back on IBM. It goes through my VPN. If it is still in place, I guess. So I have three bookmarks here. One is the Elasticsearch indices. So you guys can see that it's a small letter, but you can see that there are indexes for metric bit, and it's kind of most used way or for organizations of once a day, right? So I have a once a day index for metric bit, once a day for Logstash. The metric bit gets in-band data from agents running each of the endpoints, from the metric bit agent itself, right? And the Logstash indices, they get collection from file bit. The log files we get from those most important Linux log files, right? And it gets the alerting data from Crassd as well. So we cram all together in these Logstash indexes. You could configure it differently. If you want to separate the indexes in a different way, you could changing the variables in the Ansible playbook, right? Then there is the bookmark for the dashboards on Kibana, right? So a little bit until it loads. And because firmware data is not as frequent, at least alerting data, right? It's not as frequent as other kinds of alerts. You guys can see that I have a large period of time here that I'm visualizing, right? So I'm visualizing year to date. I could have forced generation of more log files if I wanted, but I did that a long time ago. So I just wanted to show those logs that I forced for the generation, just to give an example, right? These are alerts that are coming from the firmware itself. So if you have a situation of a high temperature, for example, it's going to generate an event and it's going to come here, right? And this dashboard, it's a simple dashboard. It has the list of events in here, so you can filter in Elasticsearch by keywords or whatever you want. Then I created like just a small visualization per type and severity. So severity is critical, warning, or something. So you can just click on them and filter by that if you want just to see the critical events, right? And then the types of events you might be interested on just the events for memory, for example, or the unrecoverable events. So you can filter out from here as well. Then I have another small visualization. There is a small flag in this in all the firmware events, in firmware alerts, that if they are call home eligible, and then there are other applications that make use of that, right? and if they are serviceable or not. So it's just another visualization showing the division of the events, how they classify per that. And then there's the top 10 sensor types of events in here. There's another one that is per source. So you can see here that here's the Boston one. So it's showing IP address because on my configuration file, I just had the IP address instead of the name. But and you have to make sure that it has a DNS backing for that. And then there's the TUMI hacks that I added later. It gives more types of alerts in here. So you can see that I think most of the events are MIHAC 1 and the Boston. This one has little, small number of events. Then there's another field on the alerts. It's called subsystem, and it tells which component of the system the alert is about, right? Then there's a state, so you can filter through all that. And then just at the bottom, I just put a heat map for the kind of the biggest hitters of alerts. So you can see that this number 1 here means core number 1, right? So core number 1 is the one that is having most problems. I don't know why. Didn't analyze yet. Then there's other cores and the gems, so you can see which component might have a lot of events and if might need to be changed, and if it has unrecoverable events associated to that or not. And then there's a similar kind of a visualization, but it's just a cloud tag map. So the biggest fonts go to the ones that get more alerts, right? So, like I said, it's a simple dashboard, but it gives you a good summary of what's happening at the level of firmware. So you can see by event type, severity, etc. So that's the Crassd alerts. Let me see how we're on time. Okay, 3 more minutes. I'm going to go quickly over the other ones. Okay, let me just show these 2 quickly because they're not as important. These are for the in-band data that is collected by file bit and metric bit. I created a simple dashboard just to show where the log events come from. So this visualization is per source of the log. So you can see if it comes from the messages log in Ubuntu or it comes from the syslog in Red Hat. There's the kernel log, there's the out log, etc. And you can see as well that this produces a lot more events than firmware events, of course. Divided by the family of operating system they came from. It's interesting to visualize if you have a mix of operating system, which ones, because usually in production, these operating systems, they're also configured by something like Ansible or Puppet or something like that. So if you have a big imbalance between events that come from Ubuntu versus Red Hat, you might need to do something in your configuration for Ubuntu, for example, to make it less prone to problems, right? Then you have events over time, event distribution, if it is a message or something from installation of a package. So that there are types of events, right? So if it is an authentication event, and then per source as well. So it's something very simple, just to get started, right? Then the other one in Kibana, it was reused from the metric bit dashboards, the standard dashboards. They didn't run smoothly off the shelf in this environment. We had to do some tweaks. But if you guys seen that before, so they have a big summary dashboard that gives you an idea of how much load you have on the whole cluster. So these are numbers for the whole clusters, not on a single system, for a single system, right? And then you can dig into CPU consumption, memory, etc. So can have a visualization. You can see that it's not been long since I started this cluster here. So it's been collecting data just for a couple of days. And etc. Has memory, has metrics for processes that are running. Here on memory, the left side is swap. And these endpoints, they're configured very, very simply. So they have no swap space. That's why we're not seeing anything here. So network, I/O throughput, storage, file systems, utilization, right? It is similar to metric bit dashboards, if you guys seen that before. And lastly, I wanted to show just what we did on Netdata to get the telemetry from Crassd, right? So in Netdata, there are several plugins that you can get turn on or turn off. So they give several metrics on CPU, memory, and it's more real time. It's different from Elasticsearch that you collect lesser amount of metrics, but you store them over a long time, right? So you dig deeper into a particular problem, you can see what other characteristics are influencing the problem in Netdata. So these things are all default plugins that come from Netdata. So monitors disk, etc. So it's all in-band stuff as well. And then the out-band stuff, the telemetry that comes from Crassd, it's so we just create a section for each of the systems that we're monitoring. So there's one for, it's very small font. You guys are probably not seeing, but this one is a section for the MIHAC 1. And then there's a section for the MIHAC, the second MIHAC. It's actually MIHAC 9, the name of the node, right? So it gives five very important metrics, the ones that are utilized by that cooling intelligence system on the Summit supercomputer, right? So there's a current this data is coming every second. You can, of course, configure that, but if you, it depends on your application. If you want to have a response time that is quickly on the cooling plant or something like that, you need to collect data on a more frequent basis, right? So there is a current utilized. There is the fan tach speed for the multiple fans. You can see that they have many different fans on each system of this. There's power consumed in multiple sensors. So you can see what's being consumed. You can see there are some fluctuations sometimes, but if you see a large fluctuation in power consumption, it means that you need more cooling, right? There's temperature sensors all over the system as well, and then there's voltages. The power supply is the biggest one, and then there are voltages of the processor, memory, etc. So these five are very helpful in order to manage your data center, right? That combined with the metrics that you collect in band, you can correlate things together, you can do all sorts of useful stuff with them. Okay, that's what I had. So before we go to questions, just 1 second, I just want to show this for just 1 second. So these are next steps, and there are two important things that we're going to do, right? So one is to grow this project in the power community, and it's not only the traditional power users, like the legacy ones that still use AIX, but also the new ones that use the Power LE systems, a little Indian, right? Run Linux and run all these modern tools already, right? So we want to kind of foster collaboration with these teams. We want to foster collaboration with the contributors of the tools themselves. If we can get support for power, we don't need to build then on the fly on the project here, right? So it will be much easier if was already being supported upstream, the binaries and everything that is needed for power. And then the second part here is we want to enhance this. We want to add new tools. We want to add new environments like containers. We're working on that. We want to add, I don't know, deployment over Power VM for the legacy guys. So, and we want other people to collaborate as well, right? So, and lastly, we want to add support for more stuff, more goodies. One thing that a lot of people needs alongside Power is GPU monitoring, right? So we want to add GPU monitoring both in band and out of band as well through the BMC and through the operating system. We want to add support for other equipment, the storage side of the equation. So there are several tools that already do this kind of monitoring. So we want to test this and make sure that it works well on Power, right? And lastly, currency. So we're working to support newest Elastic stack now. We want to support AIX as an endpoint for the legacy guys. We want to support more beats and, of course, other tools. We want to always get support as much current as possible for the tools, right? The latest releases for Elastic, Netdata, and later Prometheus, Grafana, so we want to start supporting those as well. Okay, so that's what I had. I think we have very little time, 5 minutes for questions and answers. So, anybody? Yep.
Yep, just a second.
Thank you very much. Is this a replacement for ITM from IBM?
No, it's not a replacement. If I say it is, they're probably going to kill me. But we recognize that there is different communities, right? And we want the environment itself, Power Systems, because they are very important for some kinds of applications, AI, analytics. We want to plug the entry level of effort that it takes for you to run these modern tools into that platform as well, right? There is still going to be a niche for users of ITM, and then for users that are more open source kind of users, right?
Any more questions? Okay, we're short on time, so that's fitting. First of all, thank you to our speaker.
Yeah, thank you.